Hello everyone, I am Dipanita. Welcome to the 12th interaction session of Fundamentals of Electrical Engineering. In this week, sir has taught about the three-phase induction motor and DC motors and generators. So my colleague has covered the part of the three-phase induction motors, and I'll be covering the part of the DC machines. So we'll be solving a few questions on the motor and generator. So the first question we have for today is that a 4-pole wave-connected DC generator generates a voltage of 230 volt, and the winding initially which was a wave connected is now made into a lap connected. And what will be the induced EMF based on this type of construction? Now, in case of a generator, the induced EMF which is getting generated per conductor is given as d phi by dt. It is directly proportional to the d phi by dt, right? Now, this d phi we can relate it to be the flux that that is cut per conductor in one revolution, right? So d phi can be written as the poles, the magnetic poles, which in this case is 4 times phi, and the the number of revolutions in 1 second is given by, say, revolution in 1 second is given by n by 60, right? So the time for one revolution is the reverse of this, that is 60 by n, which is equal to dt. Now, if we write the equation of the generated EMF per parallel path in the armature, it will be given as E is equal to d phi, which is P into phi, time divided by dt, which is 60 by n. So 60 will be the numerator, 60 by n will come up, times Z by A. Here Z is the total number of armature conductors. And A is the number of parallel path in the armature. So in case of the two connections which are given, when depending on that, A will be, if it is wave connected, A is equal to 2, and if it is lap connected, A is equal to the number of poles. So in this case, in the first connection, when it is wave connected, A will be equal to 2. Now rest of the parameters can be treated as a constant, like the only the due to the connection this A value will change, whereas the total number of armature conductors will remain the same, the number of poles will remain the same, and the flux and the speed will remain the same, as nothing is given in the question regarding it. So E can be written as inversely proportional to A. So E1 by E2 can be given as A2 by A1, right? So in the first case, so it is given as 230 volt DC. So 230. Now the induced EMF we have to find out. A2, which means in the second connection it is lap connected. So in case of lap connection, A is equal to the number of poles. So it will be 4, and initially it was wave connected, so it is 2. So E2 will be equal to 230 by 2, which is equal to 115 volt. So the correct option is option C, 115 volt. So we see when everything is constant, that is when the number of poles are constant and only the type of connection changes, the induced EMF will also change. So in case of the lap connected construction, it is reducing. So I hope this is okay with you all. If yes, then we'll move to the next question. So for the next question, it is given that a DC series motor is driving a load and the magnetic circuit of the motor is saturated. Now what does this mean, that magnetic circuit of the motor is saturated? It means that increasing an air, like when we are increasing the external magnetic field, it can no longer increase the magnetization of the material, which is the core material, and as such uh, like the flux is kind of constant. So in this case, if we are to write the equation of torque, we know torque is given as, so torque is proportional to phi into the armature current, right? Now this phi is constant, since in the question it is given the motor is saturated, so torque is proportional to Ia. Now also it is given that between the load torque and the speed, the relation is given by TL equal to K times omega to the power 1.5, where K is a constant. So the other equation we have is equal to TL is equal to K into omega to the power 1.5. Now it is given that for a speed of 350 rpm, the motor line current is 18 ampere. Now in case of series motor, the line current is equal to the armature current, so which is equal to 18 ampere given for speed equal to 350 rpm. Now for a speed of 560 rpm, what will be the line current? So if we write like for example in the first condition, when speed is 350 rpm, if the torque be T1, and for our 560 rpm if the torque be T2, which will be equal to Ia1 by Ia2. Also T1 by T2 is equal to omega 1 by omega 2 to the power 1.5 from the relation that is given in the question. So from this first equation and the second equation, we have that Ia1 by Ia2 is equal to omega 1 by omega 2 to the power 1.5. Now for the first case, when it is running at 350 rpm, we have the current as 18 ampere, and for the second case we have to find out the current. This is equal to 350, which corresponds to the 18 ampere line current drawn, and omega 2 is the new speed for which we have to calculate. This is 560 to the power 1.5. So so we can calculate now Ia2. It is 560 by 350 to the power 1.5 into 18. So let us calculate this. Five 60 divided by 350 to the power 1.5 into 18. This comes out to be 36.429 amperes. So which is equal to the option A, which is 36.43 ampere, right? Everyone got this? If yes, then we can move to the next question. No questions, right? Okay. So for the third question, a DC shunt motor which is delivering a power 60 kilowatt at 300 volt with a prime mover which is rotating at 500 rpm. The armature and the field resistance is given as 0.5 and 0.02 and 50 ohm. We have to calculate the speed of the machine when it is running as a DC shunt motor taking a 60 kilowatt load at 300 volt. So initially the machine was running as a generator and it was delivering power, and the same machine now is running as a DC shunt motor which is taking a load of 60 kilowatt at 300 volt. We are neglecting the armature reaction and the like the brush drops. Now the armature reaction is basically the effect of the main field flux on the flux set up by that set up the current in the armature winding. So neglecting the brush drops, again, like there is a very small voltage across the brush that are connected across the armature. So these two drops are neglected, and for this ideal condition, the same machine is now connected in working as a motor, taking the same rated load and voltage. So what we have to find is now the speed of the machine when it is running as a motor. So let us first look into the DC shunt generator, for which the parameters are given. So in case of the generator, let this be the resistance of the field winding. So this is the resistance of the armature winding, and this is the generator. So since this is a generator, it is delivering a load, so the current direction will be equal to IL. Let this be the terminal voltage VT. The field current, let it be equal to IF, and the armature current as IA. Now at this particular node, let me denote it by AB. So at this particular node, VAB is equal to VT, because there is nothing connected in between in this line. So this load voltage will come across AB. So we will have the current across this branch IF, that is the field current, will be equal to the voltage across it, that is VT, by the resistance in that branch RF. So VT is 230 volt and the field resistance is 0.02 ohm. Sorry, the field resistance is 50 ohm, right? So sorry, it is 300 volt, not 230 volt. So it is 300 volt by 50 ohm, which is equal to 6 ampere. Now what is the load current? We can calculate, since we have the rated load, which is given as 60 kilowatt in the question. So the rated load and the terminal voltage is given. So we can calculate the load current to be the rated power, which is 60 into 10 cube, since it is in kilowatt, by 300. So this is equal to 200 ampere. Now if we simply apply KCL at node A, we have the armature current is equal to the field current plus the load current, right? So it is 200 plus 6, 206 ampere. So now if we apply KVL across this particular loop, we have minus EG plus IARA plus VT is equal to 0. So we have EG equal to VT plus IARA, right? We are applying KVL across this loop. So the terminal voltage is 300 plus the armature current is 206, and the armature winding is given in the question as 0.02. So the total back EMF that is getting generated is given by 300 plus 206 into 0.02, which comes out to be 304.12. This is 30.12 volt. Now in the previous question we have seen that the generated EMF is proportional to some constant times the speed or the RPM. Here omega is given in the question. We can find omega from the 500 RPM speed that is mentioned here, right? So let this be omega g. This is one of the equation, and we have EG here. So for the next case, when it is working as a shunt motor, let us again find the parameters. So when it is working as a motor, only the direction of the current will change, because now it is drawing a load. So in this case, so the field current will be the same. This is the field resistance, this is the armature resistance, this is the terminal voltage, remains the same. Now in case of motor, the only thing is it is actually drawing the load current. So sorry, let me just yeah. So the direction of the current, since it is drawing the current, it will change. So again, if we apply like the KCL at node A, it will be, so the field current and the armature current are leaving the terminal and the load current is entering the terminal. So IA is equal to IL minus IF. Now we have the, so for the load current, in case of the motor also, it is rated at 60 kilowatt and 300 volt, right? So still it is the same thing. So the load current will be 60 kilowatt, the power, divided by the voltage 300 volt, which is 200 ampere. And what will be the uh, field current? It will be the applied voltage. Here again it is 300 and the resistance of the field remains the same, which is equal to 50. So it is again 6. However, now since the equation of the armature current has changed, so it will be 200 minus 6, which is 194 ampere. Now when we apply KVL in this particular loop, let me use a different color. So when we apply KVL in this particular loop, for the motor, the equation that we get is the back EMF is equal to terminal voltage minus the armature drop. So it is 300 minus IA is 196, RA is given in the question as 0.02. So the back EMF that we get is 300 minus 196 into 0.02, which comes out to be 194, sorry. This is 194. So it is 296.12. Now we have to find, so we have again EB proportional to, let this be the motor speed. So we have to find this quantity, we have this quantity. So in the generator case, so EG, which is some constant, into WG, and in the second case it is EB, again proportional to WB. We have these three values, we can calculate WB, right? So from the previous case we have EG equal to 304.12, right? So 304.12, EB is calculated as 296.12. The generator speed is 500 RPM. So 500, and we can calculate WB. So WB is equal to 296.12 by 304.12 into 500, which comes out to be 486.84. So let us see, 486 is in the range which is given in option B. So option B is the correct option here. So I hope this is clear to you. If not, you can ask right away. Otherwise, we will move to the next question. So, is this clear? Okay, then we'll move to the next question. So, in the fourth question, a 15 kilowatt 230 volt DC shunt motor having an armature circuit resistance as zero point 0.4 and field resistance as 115 ohm is given, and at no load the rated voltage of the motor is said to be running at the rated voltage the no at no load and the rated voltage the motor is running at 1400 rpm, and the line current drawn by the motor is given as 5 ampere. At full load the motor is drawing a line current of 70 ampere, and neglecting the armature reaction, what we have to do is find the full load speed in rpm of the motor. So this is again a DC shunt motor. So like we did in the previous problem, the shunt motor circuit is as shown here. So since this is motor, it is drawing the armature current. This is RA, this is field resistance, and the field current is flowing. So this is the armature. Let this be the back EMF and the terminal voltage. So this is the load current that is drawing. So we are given RA and RF. So this terminal voltage is getting applied across this node A and B. So we can calculate the field current, right? So the field current will be the terminal voltage, which is 230 volt, by the field resistance, which is 115 ohm. So this is equal to 2 ampere. Now the load current is given as at no load the line current, sorry, not the load current, the line current that is getting drawn is 5 ampere. So this line current is now 5 ampere at no load. So if we apply KCL at node A, so we have the armature current is equal to the load current minus the field current. So at no load, the armature current, let us denote it by INL, is equal to the line current at no load, which is equal to 5 ampere, minus the field current, which is 2 ampere. So this is 3 ampere. So the back EMF that is getting generated at no load, let us denote it by EB, no load. So it is given by the terminal voltage minus the armature current at no load times the armature resistance, which is 230 minus 3 into 0.4. So this is 230 minus 1.2, that is 228.8 ampere. So this is the situation at no load. Now at full load, the motor is said to draw a current of 70 ampere. So at full load, the armature current will be the load current, the line current at full load minus the field current. So field current will still be 2 ampere, because that much because it is directly across the terminal voltage. So now this is 70 minus 2, that is equal to 68 ampere. So the back EMF at full load will be equal to Vt minus the armature current at full load into the armature resistance. So Vt here is 230 minus 68 into 0.4. So let us calculate this. Minus 68 into 0.4. This is equal to 202.8 volt. So now we have the back EMF at full load, back EMF at the no load, and we have the speed at the no load condition, right? So we know that EB is directly proportional to omega. So EB at no load by EB at full load will be equal to omega at no load by omega at full load. So we have to find this omega at full load. So omega at full load will be equal to E at full load, which is 202.8 by EB at no load, which is equal to 228. 8.8 times omega at no load, which is given as 1400 rpm in the question. So let us calculate this. 202.8 by 228.8 into 1400. This comes out to be 1240.9. 1240.9. So which comes in the range as given in option D. So option D is the correct answer for this question. These questions are pretty much straightforward and kind of similar. It is only the motor and the generator equation and the direction of current which matters. I hope you have got this. If yes, then we can move to the next question. Okay, let's move to the next question then. So for the fifth question, we have a 270 volt DC series motor which takes a 45 ampere current when it is giving a rated output of 1500 rpm. Its armature resistance is 0.1 and the field resistance is 0.2. It is found that to obtain the rated torque at the starting, a resistance of R1 has to be added, and in order to obtain the rated torque at 1000 rpm, a resistance of R2 has to be added. So we have to find the value of R1 and R2, neglecting the voltage drop in the buses and assuming that the magnetic machine is to be unsaturated. So note that in this question, the magnetic circuit of the machine is unsaturated, which means torque depends on phi and Ia both, and this phi A, since it is not saturated, so it is non-constant. Now we also know that phi again is proportional to Ia, so torque is proportional to Ia square in this particular question, as opposed to what we have done 2 questions back. So for this question, what we have to do is first the thing to know about in case of series motor. So this is an external resistance that is connected. This is the series resistance. This is the armature resistance. So in case of a series motor, this external resistance, let me draw it first. So yeah, this is the terminal voltage. This is the motor back EMF. Okay, so this external resistance, when the circuit is at rest, in order to start the motor, this external resistance is at its peak, and gradually as the motor attains the speed, this external resistance is reduced, and at full load, like for in this case, when it is given that at the rated output of 1500 rpm, at this case this R external is 0. So let us consider at when the DC motor is taking 45 ampere and it is running giving a speed rated output at the speed 1500 rpm. So in this case, the full load current is 45 ampere, the line current is 45 ampere at its rated load, and the speed is 1500 rpm. So we have the equation EB is equal to Vt minus Ia into R equivalent. Equivalent means the summation of all this, because by applying KVL we get this equation in this loop, right? Now at 1500 rpm, that is at rated load, let us calculate the back EMF. Let this back EMF be back EMF rated. So at this VT 230 is 270, it is given 270 in the question. So, and the current that is getting drawn here, in case of a series motor, the armature current is equal to the field current is equal to the line current, right? Which is given as 45 ampere. So this is given as 45 ampere in the question. So it is 45 into R equivalent now only consists of RAC and RA, because it is giving at the rated output. So the external resistance is not there. So it is 270 minus 45 into the armature resistance is 0.2 and the field resistance, series resistance is the field resistance here is 0.2 and the armature resistance is 0.1. So let us calculate it. 270 minus 45 into 0.3. This comes out to be 256.5 volt. Okay. Now so let us calculate one by one when at the start when resistance is R1. So when the motor is at rest, like it is just about just to be started, there is no back EMF generated because the motor has not started yet, and omega is equal to 0, right? So in this condition, if we apply like in equation 1 where EB is equal to 0, so VT terminal voltage is present minus IA into R equivalent. Now in this R equivalent, it consists of the resistance R1, which is given in the question, that it is found to obtain a rated torque at starting. A resistance of R1 has been added, which is given in the question. So this R equivalent now consists of R1, R series and armature. So let us calculate R equivalent first. R equivalent is equal to 270 by IA, that is 270 by 45. So it is 6 ohm. So now this R equivalent consists of R1 plus R series and R armature. Now we have these two values, which is equal to 0.3. So from here we can calculate R1 is equal to 6 minus 0.3, that is 5.7 ohm. Now in the next part where it is given to obtain a rated torque at 1000 rpm, a resistance of R2 has to be added. So in this particular case, we have to again calculate the back EMF, and we can equate what we got at the rated the back EMF at the rated, which is given by 256, and we can relate it in terms of the speed of rotation, and we can calculate the value of R2. So I'll just take a slide here. Yeah. So for this, sorry. Now similarly in the next part where torque is given, where it is like it is giving out the rated torque at 1000 rpm, we can calculate the back EMF. Let this be EB dash. EB dash equal to VT minus IA into. So since we do not know the value of, let us not use this equation. So yeah, So for the first case, we have the value of EB, right? So we know EB is directly proportional to W. So in the case when it is rotating at 1000 rpm, let this it be EB dash. So EB by EB dash, this is the rated one, right? We have is equal to omega rated by omega dash. Now omega rated is given as 1500 rpm in the question. So we have EB rated is 256.5. We have calculated this. 256.5 by EB dash is equal to rated is 1500. Yes, 1500 by omega dash. Omega dash is 1000. So we have the value of EB dash to be 256.5 into 10 divided by 15. That is 171. Now we can easily equate this in the equation. So we have EB dash is equal to VT minus IA into R equivalent. Now this R equivalent, since EB dash is the back EMF when it is rotating at 1000 rpm, so this R equivalent will consist of R2 plus R series and R armature, because in the question it is given to obtain a torque at 1000 rpm or resistance R2 has to be added. So we can calculate it as 171 equal to 270. Yeah, 270 minus 45 into R equivalent. So R equivalent is equal to 270 minus 171 by 45. 270 minus 171 by 45 is equal to 2.2 ohm. Now R equivalent consists of R2 plus R series plus R armature. So R2 is equal to 2.2 minus 0.3, which is equal to 1.9 ohm, right? So let us look into the options. So option B has R1, which we have calculated here, R1 as 5.7 ohm, and it has R2 as 1.9 ohm, right? So we have option B as our correct option. So I hope this is clear to you, because this is pretty much solving the same type of problems, only here it is a series motor instead of the shunt motor that we were solving previously. So if you have any question you can ask, otherwise we can move to the next question. Okay, so for this question it is given that at no load the speed of a separately excited DC motor is given as 1800 rpm, and the armature resistance drop and the brush drops are neglected. The field current is kept constant at the rated value, and the torque in the motor is to be calculated in Newton meter for an armature current of 10 ampere. So in one of the condition it is given about the RPM, and in the next it is given as given the load current in relation with torque. So first let us write the equation of back EMF and torque and see how we can extract the values from the first information and put it in the next information to calculate the torque. So the back EMF is given, as we have seen earlier, 5P N by 60 into Z by A, right? So if we rearrange this like so in place of N, like if we write omega is equal to 2 pi N by 60. So this N by 60 we can replace it as 5P into omega by 2 pi into Z by A, right? So let this be, so omega is changing, so phi and omega are changing, and the rest of the equation, which is given by this, we put it as a constant. Now if you look into the equation of torque, which is given by 1 by 2 pi p phi ia into z by a. So in this case, you see p by 2 pi into z by a times, if we write phi into ia. So this is same, this constant is same as that we have equated it to be k. So this is also equal to k phi into ia. So torque is given by k phi into ia. Let us denote this by equation 1. Now in this case, we have the RPM, which is given as 1800. So if we simply write in this equation, let me divide this. So yeah, E is given, like the no load speed of a 228 volt separately excited DC motor. So in this case, since there is no load, so in case of separately excited DC motor, IA is equal to IL, the armature current is equal to the load current. Since it is given that this is the voltage at no load speed, so which is equal to 0. So from the equation we have EB equal to VT, the terminal voltage, minus the drop in the armature resistance. Now this is equal to 0. So EB is equal to the terminal voltage, which is equal to 228 volt. So in the first question we have E is equal to 288 volt. So we have 288 is equal to k phi into omega. Now it is given as 1800 RPM. So we have to write it in terms of radian per second, right? So it is 1800 into 2 pi by 60. So we can calculate k phi from this equation. So it will be 288 by 1800 into 60 by 2 pi. So let us calculate k phi. So it is 288 by 1800 into 60 by 2. This comes out to be 1.52788. Now from this particular equation 1, we have the load current k phi, which can be written from this particular equation and plugged in there. So we can easily calculate the value of torque, right? So torque will be equal to, k phi is 1.52788 into 10 ampere, that is equal to 15.2788 in Newton meter. So none of the option actually matches to this value. So the correct option is option D, none of the above. So this is the last question for today. So in case if you have any problem or if you have any query, you can always mail me. So I hope you have understood everything. Most of the topics have been covered by sir by now. So I guess this will be the last one. In case if you have any queries about any specific questions, you can always mail me. This video will be uploaded in the YouTube link, which is shown here, and the lecture notes will be uploaded here. So thank you all for attending. I hope you had a good time in this course. Thank you.